So I'm going to introduce our speaker, Debbie Hutchinson, from the US-GS in Woods Hole. She came to Woods Hole, the US-GS there at Woods Hole in 1974, which turned out to be about the middle of my graduate career at the Oceanographic. So I've known her for quite a while. She was able to, she came right from Middlebury College, fresh out of undergraduate education. She was able to go to the University of Toronto for a master's degree and the URI for a PhD, and is now solidly in the research trend. She's been branch-headed Woods Hole at the US-GS and knows all about that part too. Today she's going to talk to us about the law of the sea and some of the ways the U.S. is pursuing its rights to underwater lands. Yeah, this is a fighting issue worldwide, so it's something that's a little below the radar, but that we have to know about.
Roger, announce the student.
Oh yes, so we'll have lunch after, and at about 1:30, I'd like to sort of transition to a student meeting, so it'll be before the class that many of you go to at 2, and Debbie will have to tell you all she knows then too. Okay, so Debbie.
In addition to talking about law of the sea, she also offered to discuss job opportunities with the US-GS and what she knows about life after graduate school.
If I can remember life after graduate school.
So you're going to...
Yeah, I've got, this is on.
Okay, good.
Yeah, this is on. Can everybody hear me?
Yep.
Okay, so today I want to talk to you about some work that's been going on for the past 5 years in the Arctic, jointly between the U.S. and Canada. When you work in the Arctic, because it's such a remote environment, you actually rely on many other people to help get the work done. And so in this case, I want to acknowledge the many collaborators that made the project possible. On the U.S. side, it's NOAA as well as the US-GS, the US ECS Task Force, and the US Coast Guard. Our equivalents on the, I guess I shouldn't forget the State Department since it's an international treaty, but on the Canadian side we had their Foreign Affairs, we had the Department of Environment Canada, which has the hydrographers equivalent to NOAA, the Canadian Coast Guard, and of course the Geological Survey of Canada, who are the people that I've actually worked most closely with on this project. And some of the actual people are listed here who have participated in this. So even though I'm talking, it's very much a joint project. This view of the Arctic is the view that is generally given when with the Greenwich Meridian as being the central point, but as you can see, Alaska up here and the area I'm talking about are upside down. So the first thing I want to get straight is that I'm going to rotate this around, and now here's Alaska and the Canada Basin, and I'm going to try and do all the other maps there, so north is actually up for us. So there's kind of 3 parts to what I'm going to talk about today, with a kind of an ending. I'm first going to tell you a little bit about law of the sea, why we're doing the work. Secondly, the challenges of doing underway data collection in ice, i.e. operating on ships that are moving, and then give you some really pretty broad-based results from the work we've done, mostly because if I'm going to talk about these guys, I don't have a whole lot of time to talk about these. But I will raise some of the questions that have come out of our data, and that may give you a chance to see some of the more detailed work that's going on. So law of the sea. Prior to the 20th century, rule on the oceans was pretty much given by who had the biggest guns. And generally those big guns only shot 3 nautical miles, those big cannons, and so that is actually where our 3 nautical mile boundary comes from for the states. It turns out that during the 20th century, the First and Second World War, people actually said, you know, fighting on the oceans may not be the best way to go. And so the law of the sea was negotiated through a series of conventions that started in the 50s and ended in 1982. And the treaty, and it is an official treaty, is called the Constitution of the Seas, and it sets forth this legal regime that covers many aspects of what happens on the oceans: contamination, pollution, the environment, navigation, transit, rights, the whole bit. My interest and where the geology comes in is much more limited. It deals with how you manage, conserve, and use the sea floor and the subsea floor. This is a passive, the typical continental margin, in this case probably more a passive continental margin. But the treaty lays out that coastal states, meaning coastal nations, states with a capital S, have a continental shelf that's theirs to develop. And it's not necessarily a shallow water shelf, it's a legal shelf. And then there are the high seas for the heritage of mankind, for the benefit of mankind. The question is, where do you put the boundary between them? The treaty lays out that coastal states can get to 200 nautical miles or common maritime boundary if you happen to face another country. But they allow that there are resources and other potential interests beyond 200 nautical miles. And they came up with a mechanism to define what that boundary is, and that's Article 76 of the Convention. It defines how you figure out where the continental shelf ends and the high seas begin. Again, it's a legal continental shelf, a legal construct of where your rights are, not a geological one. Why does it matter? It obviously expands the land area of a country if you can go beyond 200 nautical miles. It gives you certainty in where the boundary is, which people like the State Department think is, and obviously the military think is important. I think most importantly, it gives you sovereign rights over your resources, and those sovereign rights actually are the specificity and certainty to protect, manage, and utilize or conserve those resources. And they include only things on the seafloor or below, energy, mineral, biologic, sedentary biologic. So I've alluded to some of these differences in terminology. A geologist looks at a continental margin and she's a shelf, a slope, a rise, and an abyssal plain. The lawyers look at the continental shelf and the continental margin, and they see the baselines, the territorial sea, the contiguous zone, the exclusive economic zone, which is laid out as the continental shelf, and then the deep ocean, and then the area that we're most interested in, this extended continental shelf, and that's the seafloor beyond 200 nautical miles, where this coastal state, coastal nation, has sovereign rights. How do you determine where the extended continental shelf, the ECS, exists? I'm not going to go into the details, but the treaty, Article 76, lays out two formula lines. They begin at again, a legal foot of the slope, it's called, and you can take either a bathymetric formula or a sediment thickness formula to find an outermost line. In this case, bathymetry is plus 60 nautical miles. The sediment thickness, as you go to where the thickness of the sediments is 1% of that distance. Bathymetry formula is intuitive, easy to map. Sediment thickness is not, because you have to know the foot of the slope, the distance, and the thickness. You can't just play around with maps to do that. But you can use either one in any order for whichever is more beneficial for you. But you can't go forever. You have to limit yourself, and they give you two constraint lines. One, you go from the baselines where you measure 200 nautical miles and you can go out to 350, or you take the 2,500 meter contour and go 100 nautical miles. And again, whichever of these is further out, you can use in any order, but you have to stop at the constraint line if your formula reaches the constraint line. You have to stop at the formula line if it doesn't. And so you map, the idea is to map these various boundaries. So not only do you need some way to map sediment thickness, you need a way to map the morphology and bathymetry. There are a few other things. The treaty, Article 76, deals with ridges and how you interpret ridges and how these various things apply to them. You're supposed to have natural components, so there's a bit of geology in there too, but I'm not going to go over that. So as of 2009, when this map was created, these orange areas show where nations have proposed that they have an extended continental shelf. There is a commission that is made up of scientists from within the member parties of the treaty who make recommendations as to whether they agree or don't agree with what a nation submits. But there are large parts of the ocean that that could actually be extending continental shelf. Since 2009, there's a number of other countries that have made submissions, so there's actually even larger areas. Canada will be making their submission in less than a month. You have a 10-year window after you ratify the treaty to make a submission. Theirs is coming up on December 6th. Denmark will finish their submissions in 2014, later in the year. The US has not yet ratified. We don't have our 10-year limit, but at some point, the State Department said, you know, if all these other countries are figuring out where their extended continental shelf is, we should know where it is too. But we have no idea whether our current dysfunctional Congress, and that's offline, is going to ratify any treaties, much less law of the sea. So where does the United States have an extended continental shelf? We've identified a number of areas around islands, around continental margins, where we think there's an extended continental shelf. Two areas that are probably the largest, that we're most confident about, are the Atlantic and the Arctic. And the Arctic is what I want to talk to you about for the rest of today. So if you go to the Arctic, you can imagine that if you are Canada and you want to go beyond your 200 nautical mile limit, Canada being here, you're going to go west. And if you're the United States, going beyond our 200 nautical mile limit, you're going to go north. So we have areas of overlap, as yet undetermined, but this is a remote area in an ice-covered ocean where it made sense to work together. Working in the ice is not easy, and as I'll show you in this next section, going on to underway data acquisition in the ice. When you get stuck in the ice on an icebreaker, the way you usually move forward is you back the boat up, and it's got a lot of weight in front of the boat, and you go forward, it breaks the ice, and then on you go. So that's called backing and ramming. If you're trying to collect any kind of underway data with gear in the water, you can't back up because it'll get wrapped up in the prop, so you have to take it in and out if you're in a single ship mode and you get stuck in the ice. So the idea between our two countries was that the U.S. has the Coast Guard cutter Healy, which has a multi-beam system on her hull, so she doesn't have to worry about gear being in the water when she backs and rams in the ice. And the multi-beam, as many of you probably know, is a swath mapping system that gives you this ribbon along the seafloor of what the morphology of the seafloor is, which is important for looking for the foot of the slope and the 2,500 meter contour, and you can create all kinds of beautiful images of features that you find, in this case, a seamount. And then we have the seismic system. Seismics operates with gear in the water, and consequently the idea was if the U.S. contributed at the icebreaker that had the multi-beam system for mapping morphology, Canada has the icebreaker for the seismics to measure sediment thickness. It's a match made in heaven. We both win because we both share in the acquisition of the data, and we both share in the data that we're both interested in. So what consists of the seismic system? This was a multi-channel seismic system, not unlike what industry uses, although a high-res system. Everything is in duplicate, in this case 2 compressors up on the helo deck. That makes the air that generates the sound source for the seismics. These are the air guns that were towed off the back of the ship, 3 guns, 2 500 cubic inch ones, one 150, total volume 1150 for comparison. Industry is usually around 6,000 cubic inches of air. If you're doing coastal work, you're down around 15 or 40 cubic inches of air. So this is a reasonably high resolution system. It was a digital streamer, small volume, about 100 meters of active section. When we put in the lead in and the drag at the end, about 300 meters of stuff in the water. It's too complicated and takes too much time getting stuff in and out of the ice to do anything much longer. So this is really short and high res. And then the most important part of the vessel, of the operation, is the lab where all the acquisition took place, very close to the stern of the vessel, which is where everything was deployed. And here you just see one of the watchstanders with the various computers. Everything was computerized and could be monitored from the lab, although periodically there would be checks on both equipment in the water and compressors and the like. So how does the seismic reflection technique work for those of you that aren't familiar with it? Here's a sound source, here's the receivers, the streamer, and you make a sound and it goes down and it bounces off the various layers, and it gives you an image of the seafloor and the subsea floor that looks pretty much like a cross section. So here's our, in geological terms, our continental shelf slope and going down on the rise with all the various horizons in here. Again, fairly easy to understand. Distance across here, and this is travel time, the time it takes to go down and back up on your vertical axis. In contrast, refraction, which we also need, I'm just going to get rid of that one so you're not too confused by moving lines. We also need, because it gives us velocity. Reflection gives us time, but we need velocity to convert it to depth to get sediment thickness. So refraction, I'm not going to say too much after this slide, but it sends the same signal into the water and it travels horizontally to an instrument that's fixed in time, so the ship steams away, you get further and further away. These records are not as intuitively obvious to interpret. You have a vertical reflection here, which is what would make up your reflection record, and then you get progressively wider angle reflections until you get these diving waves, the ones that travel horizontally. In our case, we actually had sound buoys in the water. We couldn't have instruments on the seafloor because you can't release them and get the data back because they might come up under the ice. So we actually had something floating, so actually the signal comes back up. But it's with the refraction data that we get other information from the seismic system that gives us velocity. So there are problems collecting data in the ice. This is in open water, reasonably open water, the video, oops. Let me see if I can get this guy going again. There we go. That's the air gun sled with, you can see the air gun's going off, the bubble pulse, and it moves along and it's fine, everybody's happy. But you get into heavy ice conditions and various things happen. Your seismic signal goes off and all of the energy goes into the air, and that's not what you want. So there are challenges in just moving through the ice and making sure that doesn't happen. In this case, icebreakers have 3 props. That was a middle prop that was also strong enough to push the 4,000 pound sled almost totally out of the water. So there was a learning curve there. Yeah. So on which props to use when you're collecting data. So the 2 icebreaker experiment proceeds in light and moderate to heavy ice with the Healy in the front breaking ice, in this case pretty light ice, and the Louis following behind with its seismic system. At some point you get into very heavy ice where it's just too dangerous to have the seismic system going because the ice closes in so rapidly behind the ship that you have no cushion for pulling the gear in and out if there's a problem. In those situations we tended to haul the gear off of the Louis, and then the Louis would lead the Healy so that the multi-beam data would be better quality. So the Louis would break ice. These were typically when we were headed on to the Canadian continental margin. This is a ice radar satellite map, and it shows all the individual ice flows here. This is a line we were doing onto the Canadian margin to try and get the both sediment thickness and the morphology information. So here you can see we went around a large multi-year flow, so we didn't have to break the ice, and then our line kind of wiggles back and forth looking for the leads in the ice. These are 12-hour marks here, and you can see as we get into heavier and heavier ice, they get closer together, and the 2 ships are going slower and slower, and then we reach a point where we're going so slow, the ice is so heavy, that we go into this configuration to go onto the Canadian margin. And you can go much faster when you don't have the gear in the water. You still have to break the ice. But anyway, that's essentially how the experiment works. So now I want to turn and give you some of the science problems, because those of us that are scientists, we're sort of interested in mapping sediment thickness, but we're really interested in doing the science that goes with mapping in a frontier area. So just to locate some of the features that I'll talk about, these are various nations around the Arctic, 5 nations: Denmark with Greenland, obviously Norway, Russia, US, and Canada. The Gaggle Ridge is the continuation of the Mid-Atlantic Ridge system going into the North Atlantic and coming into what's called the Eurasian Basin. It is a Cenozoic young and well understood rift, ultra slow rifting, but it's got seafloor spreading anomalies, fracture zones. Started, what, 55 years ago or something, pretty well understood. Lomonosov Ridge is a fragment of continental crust that rifted off of the Eurasian margin right here when the mid-ocean ridge propagated north from this part of the Atlantic. So it's a relic fragment isolated in the middle of the basin. And there's a number of potential field anomalies that support that interpretation. There's a more amorphous feature going across the Arctic, the Alpha Mendeleev Ridge system. It's sometimes called the Alpha Ridge and the Mendeleev Rise. This has been interpreted, and I'll show you a little bit later on, as a large igneous province, a very large mafic body in the crust. The Chukchi Borderland is an area that we were interested in because a good part of it is likely within the US extended continental shelf. It is a submerged body. I think it goes anywhere from 800 to more than 1,000 meters depth, but its attachment to the Chukchi shelf has been interpreted that this is a continental microfragment that's isolated in the Arctic Ocean. And then the area that I will be talking about as well is this is the Canada Basin, the area between the US, the Canadian Arctic Islands, the Alpha Mendeleev Ridge system, and the Chukchi Borderland. Prior to our going out, there was very little data, certainly seismic data, collected in the Canada Basin. This is the distribution of lines, and you can see in the main part of the Canada Basin, there was almost nothing. Some of these were lines from the 70s, some from the early 90s. I think these were from the 60s Ice Island experiments, and then one 2005 experiment that went across the Arctic to between Alaska and Norway. But single ship, and so the lines get shorter as the ice gets heavier. When we were done, after our 4 two-ship seasons, 2008 to 2011, we had filled in many large gaps and have actually a pretty good coverage here. We had about 15,000 kilometers of multi-channel data, including a line that comes off Chukchi, and we got within 90 miles of the pole, 90 nautical miles, but we didn't have a scientific reason for going up there, so we had to turn around, however much everybody wanted to. 145 sonobuoys for the velocity control. Since that time, the Arctic has obviously been of great interest to many groups, and there has actually been a lot more data acquisition. Alfred Wegener Institute, 2008, collected a grid that went between the Chukchi and the Mendeleev Rise, these kind of turquoise lines. The geophysical company, Ion Geophysical, collected these purple lines on the Beaufort margin in the Chukchi Sea, and then NSF collected a grid for Bernie Copley at University of Alaska Fairbanks in 2011. So there continues to be more data getting collected there. One of the things to bear in mind, this is a large area, and there are almost no wells to constrain what the interpretation is, almost no ground truth. There are 5 wells on the Chukchi Shelf. These were done in the 1980s. There's the ASEX drilling from the 2004, I believe. There's a series of wells on the North Slope, a couple of them on the inner shelf. I don't show them. They're a similar situation on the Canadian islands, but not much that allows you to tie the offshore stratigraphy to what's in the Canada Basin. These really aren't useful for tying down to the Canada Basin because of the Alpha Mendeleev Ridge in the middle. So really, most of our control comes from the 5 wells on the Chukchi Shelf and trying to make inferences based on that and known geologic history. So one of the fundamental problems with this part of the Arctic, this Amerasian Basin as it's called, has been where is the oceanic crust? If you look at the potential field information, it's never been clear where it is. So here's the bathymetry that I showed you before. This is a gravity map, and gravity shows you density, which mimics bathymetry. You can see many of the same features in the bathymetry, but it's telling you something slightly different. You can see the Cenozoic mid-ocean ridge system shows up very well. The Lomonosov ridge shows up very well. And then the feature I want you to look at is the gravity low that comes through the middle of the Canada Basin right there. It's called Canada Basin Gravity Anomaly. And if you look at the Gackle Ridge, there is a gravity low along the Gackle Ridge because there's a valley there. And the interpretation has been, even though the seafloor is flat, that somewhere buried beneath the sediments must be the equivalent of a mid-ocean ridge. The problem is when you come over to the magnetics, you don't really see the striped anomalies that you see up associated with a more typical mid-ocean ridge. So even though there's hints of that, the region is actually dominated by the magnetic signature of the alpha Mendeleev ridge system. Magnetics respond to mafic content. It's a reflection of the mafic content in the rocks. And one of the things you see immediately is that the signature of this large igneous province, as it's interpreted, is much larger than the actual ridge system. And what that says to us is that the flat seafloor in here has basically been sediments that have covered over the ridge. So that's a pretty easy thing to see. So one of the big questions is, where is oceanic crust in the Canada Basin? Well, because there was no data in this part of the world, all kinds of models have been proposed and some dismissed. This is kind of a cartoon that's showing Alaska and Canada. Here's the Chukchi Borderland, the Mendeleev rise, the Alpha Ridge. And the red shows where various authors have proposed the mid-ocean ridge system exists. And, you know, take your pick, all over the place, because there hasn't been any real, there was no seismic data really to constrain it. It was just arm waving. What's happened in the last few years is that the interpretation of the so-called rotational model, where the mid-ocean ridge comes up along that gravity low and things have kind of opened like a wedge, has been the favored one. But this has some problems because it also has an opening on this other side of the Chukchi that hasn't been necessarily supported by the data. So that's one of the fundamental problems that we were interested in tackling. So what did the data show? This is a composite line going up the western side of the Canada Basin. Here's the Chukchi Borderland, Alaska, going around to Canada. This is distance along here, travel time along here. Here's the seafloor coming from Alaska along the very, very flat Canada Basin seafloor up onto the southern part of the Alpha Ridge up here. I've highlighted some of the horizons that it's possible to pick on this data, and then you can see basement coming up here. A few things to point out here. This is a remarkably undisturbed sedimentary sequence. There's a few faults that are interpreted here, but they're very small faults. This has been a very stable basin for a very long time. Sediment thickness here is probably about 6 to 7 kilometers, so you're looking at a very large piece of the margin. This is what, 1,000 kilometers? This is highly exaggerated, but nonetheless, you can see that sediments are thickest in the south, and they've just kind of been filling in, going north. They're oldest to the south as well. And so clearly the basin was much smaller earlier in its history as a result of that. So anyway, take-home points here, the sediments are remarkably continuous, they're older in the south. And if I bring up the next line, which is a similar profile on the east side of the basin, again, you're going from here near the Canada margin down onto the Mackenzie Delta Fan area. So here we are in the south on the Mackenzie margin, going down the same very flat seafloor and then up to the Canada margin. And you can see many of the same horizons through here, but as you get close to the Mackenzie system, the signal is attenuated because of the many mass transport deposits shallow in the fan system, and they attenuate the signal. So you can sort of see a horizontal fabric, but how you would connect each of these individuals to this fabric is is a little bit speculative. But in general, you see the same deep, shallowing to the north, probably the oldest and the thickest sediments are to the south. They're actually probably in excess of 10 to 12 kilometers here. We don't see them. There's a first multiple here, which is when the signal goes down and bounces a second time. And our basement we lose in the multiple signal, which is just much stronger than the basement. So, I'd now like to suggest that looking at the potential field data has to some extent guided the interpretation. We think in the Canada Basin that even though it's a single and looks like very stable basin through time, that there's really two pieces to it. The southern part of the basin, we would say, probably has a component of normal seafloor spreading in it. And the northern part of the basin is transitional to this large magmatic domain of what's called the High Arctic Marginis province, the HALIP. So now I want to show you a little bit more information from both the south and the north to convince you of this. This is a profile that actually goes across the basin in what we would call the southern Canada Basin. So here's coming off North Wind Ridge, here's the seafloor coming onto the Canadian margin, and here's our basement getting thicker towards the Canadian side. And that's probably because most of the sediments have come off the Canadian side. There's very little evidence that any sediments have come off the Chukchi Borderland right there. But we see an interesting symmetrical situation here of a very bright horizon that's really pretty low relief, and hints of it over here, and in the middle, our basement is very rough and very low amplitude. And it's generally symmetrical, although it's clearly deeper over here. We have same mass transport deposits coming off of the Canadian margin, probably associated with glaciation. They're probably glasogenic debris flows and turbidites, mass transport deposits coming down there. If we look at a transect that will be coming down the south side, we see a similar geometry, not quite so clear. We have obviously thicker sediments and older than we had in the transect to the north. But again, we have this more brightly reflective basement, and then this more higher relief and very low amplitude in the middle, and then we're into the region of the multiple there. But we think that this high relief, low amplitude basement is probably true oceanic crust. And it's distinctly different than what's on the edges here, and that we are probably looking at a sediment starved continent. My interpretation is that we're actually looking at somewhat of a sediment starved continental margin of the Chukchi Borderland, and we're just having remarkable ability to see into the sediments of what's going on. 2 points as a result of this mapping. I mentioned that we had the 5 wells on the Chukchi Shelf. Well, obviously one of the things you want to do is date the horizons. In this case, we have a lot of Paleozoic rocks. We're going from old to young right here, forming basement on land. The thing we are most interested in is the time frame that we think is the Canada Basin. Widespread unconformity marking the rift, the start of rifting and formation of the basin known on land, and then we think there's these various unconformities that we can track offshore. I'm not going to go into that too much, other than to show you that on this same north-south transect off of Chukchi, we actually can put these, what we think are these dated horizons, onto a map. And here's the Mesozoic sequence, and here's the Cenozoic sequence. But it's totally speculative, really. It's taking, doing a lot of assumptions to go from the Chukchi Shelf to the deep basin. But once we have these, we can start mapping thicknesses. We can map the structure maps, the tops of the surfaces, the bottoms, and that tells us a lot more about the geology of how the basin evolved. Second thing here is we can map the distribution of this high relief, low amplitude reflection that we think is representing oceanic crust. This is in the gravity map, and it's pretty much symmetrical about that gravity low. We can't see basement down here because of interference from the multiple, but to a first order, that is where we think the oceanic crust is. This is the same map on the magnetics, and it roughly coincides with where these linear anomalies are. But the key thing here is that we don't have to close the whole basin next to Canada. That seafloor spreading is only in the middle of the basin. One of the problems in the grants model is that Chukchi Borderland here, if you close the entire basin, overlaps with the Canada Islands, and that's not realistic in the opening. So this solves one problem with that. The other reason we're pretty confident that this is oceanic crust is because the sonobuoys in this region are showing velocities that are very similar to oceanic crust. This is typical oceanic crust, 2 kilometers of oceanic layer 2, the basalt layer, and then 5 kilometers or so of oceanic layer 3, which is the gabbroic layer. Turns out that these lower crustal velocities can be very diagnostic. We have sometimes see higher velocities in the lower crust. That's not typical of oceanic crust. That's typical of either underplated mafic crust or what we think in this area is hyperextended crust. It's serpentinized mantle. It's known in various called magma pore margins, and we actually think that this is probably magma pore. We have a lot of these very high velocities over here. And then continental crust rarely has velocities above 6 to 6.5 kilometers per second, except in the cratons where it can get up quite higher. So this oceanic crust in the middle, the 6.9 plus or minus a little bit, it's turning out to be a consistent story, and our work now is to combine the rest of these velocities and modify this boundary a little bit based on integrating the velocity information. So the Northern Canada Basin gives us a different picture, and I'll just go through these quickly. This is across the basin, north of Chukchi, and you see some rough relief here, but you have much different kind of basement. It's very hummocky, and again, high relief. This is something that is not typical of oceanic crust. In this probably northeastern corner here, basement goes down. This looks much more like a typical graben that you would see associated with rifting. So this northern area, we're getting out of what we think is our typical oceanic crust into something different. A postdoc that was working with me has called this bright reflection, high amplitude reflection package a HARP. If we go even further north, where we're actually closer into what we know is the alpha Mendeleev magnetic signature, you see structure, you see reflections in the basement, and you see a very rough and probably faulted basement through here. Here's the very northern edge of the gravity anomaly, and again, more hummocky stuff over there. We know there's part of the reason that it's called a large igneous province is basalts have been recovered. As part of Law of the Sea, we dredged samples here. This is a volcanoclastic one on the southern Alpha Ridge. Basalts between Alpha Ridge and Chukchi, and then a number of basalts on Chukchi as well. And then we discovered the Savaga-Tegiak seamount up in this area, a 200-meter contour on the original map. Turns out it's almost 1,200 meters high, and that's because this is a frontier area, not much data collection. So basalts are known. There are cores that got basalts in the bottom of them up on Alpha Ridge, so that's the large igneous province. We think, these have been dated at 88 to 112 million years, so they're Cretaceous, mostly late Cretaceous in age. The HARPS, this is just a close-up of them. They're some of the brightest reflections in the sequence. They rival the seafloor in brightness. Here's a case where they're highly faulted, disrupted. Here's a case where they just look like they're infilling. So the question is, are these basalt flows? Are they sills? What are they? And obviously without samples we don't know, but we think they're associated with this large igneous province. So these are just some of the descriptive parts of them. They've got clear tops, bottoms, cyclicity to them. light. Well, the postdoc working with me, Deborah, ran a model where she took alternating high velocity and low velocity layers, converted it to travel time. The idea being here that these would be the sediments on the top and this would be the basement on the bottom with this wedge of material there. If you send a wavelet through it, you get tuning, you get constructive and destructive interference that gives you low amplitudes at the top and the bottom and these very bright amplitudes in the middle. And we think the simplest interpretation here is that we're looking at interleaved high velocity basalts and low velocity sediments as an interpretation. There's other evidence, we think, of magmatism in the sedimentary sequence. This is from Rockhall, where they have 3D seismics and drilling, where they can actually see these things in much better resolution and distribution than we can, and they see basalt flows that look like this. They see sills that have this little U shape here, and then they interpret what they see are hydrothermal mounds. In the 3D data, they're actually circular mounds. And in our 2D data, I think we see a lot of similar stuff here. The scales are not exact, but they're similar enough. This could be a hydrothermal mound buried in the sediments, and this kind of offset, shimmery look to the sediments could, in fact, be fluids that have come up from this hydrothermal mound. So that's an interesting, possibility here. Again, no samples, no real idea. We see these shingled U-shaped or slightly U-shaped reflections. These could, in fact, be similar to what has been seen as sills. Again, these are up north in this northern area. So just to summarize, South and North Canada basins, the southern we think is a fairly simple seafloor spreading environment. And we think it may be magma core, though I haven't really justified that very well. And this northern area we think is the transition into this high Arctic large igneous province, where there's evidence of magmatism, probably extrusive and intrusive, and we're trying to work with the seismic data to sort some of that out a little bit better right now. So we're really in a transition zone in the north, even though it's all acted as one basin. Now just go quickly through a few slides that talk about some of the questions that we've raised as a result of this to show you a few things. This is actually a mirror image of the same profile, although this one is at a different scale. This has the stratigraphy that we've interpreted in the ages here. This is the same profile with a stratigraphy that Art Brandt's interpreted based on a constant sedimentation rate in the basin. And we can see right away that this, which is the mid-Brookian unconformity, which is supposedly the top of the Cretaceous, is offset from his. This top of the Oligocene is shown here deeper than the Eocene, and the top of the Oligocene is younger than the Eocene. So, which of our interpretations has more validity? Remote ties to these faraway wells versus an inferred constant sedimentation rate. Well, they're probably equally as good and equally as bad, but they have very different implications for the history of the basin because they're very different sediment thicknesses and geometries of the horizons at the time. So that remains to be sorted out. Secondly, an interesting thing an interesting observation that's come up, we have the Chukchi Borderland sitting right here. The Russians have published data across this mostly unknown but very large rift basin called the North Chukchi Basin on the west side of Chukchi. You can see it through here. The horizons are the bottom just basically dropped out of the basin right here. So their lower Cretaceous unit is this green one right here. I've mapped the top of our basal unconformity to the upper Cretaceous, lower Cretaceous boundary, the same unit here. It pinches out. This is our oldest unit. It pinches out as we go up Chukchi, but it thickens quite a lot this way. So it looks as though we have dramatic thickening over here, dramatic thickening up here. Why didn't the Chukchi Borderland fill in? Why didn't all the sediment fill in this deep basin right here? So that's an outstanding problem. It looks as though the Chukchi Borderland has served as a buttress to divert the early basin sediment both this way and this way. And this isn't a problem we can address. It's got somebody with data through here and on the Chukchi shelf is going to have to do that. There's actually 2 episodes of magmatism associated with the large igneous province. In some work that Arne Dossing did, he's from Denmark. This is again looking at the European view of the world. He closed up the Eurasian Basin. Ignore this right now, and I'm going to twist it around and put it in the same orientation as this. So he looked at dikes that are well dated on Franz Josef Land in Russia, coming across Greenland and the Canadian Arctic Islands, and those pretty consistently have a date that's older than what we saw with the basalts down here. These come in at 138 to 125, and they're tholiitic. So he thinks that these come from a very large volcano, possibly this very high magnetic signature up here on the Alpha Ridge. And he proposed that maybe some of these other lineaments in the magnetics were associated with the opening of the Eurasian Basin at about this same time, about maybe a little bit after this age. So we have these tholiitic basalts associated with all these sills and dikes known on land, and then we have these much younger alkaline basalts. And I think one of the challenges for our interpretation now is we have one magnetic signature, but 2 ages. And which of these is causing the magnetic signature, and can we resolve any of that in our seismics? And it's been very difficult to do that so far. So 1 magnetic province, 2 ages. Second to last thing I'm going to say here, as I've said, the basin is incredibly stable. There's very little evidence for deformation. But in some places, we actually do see deformation. This is a fault where you see offsets of similar horizons. You can see it in the stratigraphy here. This is some of the more complicated basement, the HARP, the so-called HARP. This is our top Oligocene unit. So this has affected probably pretty young stuff. And in fact, this is north of Chukchi Borderland. But if we actually go to a profile right on the Chukchi Borderland, this is on Northwind Ridge right here, you can see offsets in basement that actually could be coming up to the seafloor. This is highly exaggerated again, but so the possibility remains that we have postrift and young deformation occurring at least around the Chukchi Borderland, and there are indications of it in the Alpha Mendeleev Ridge system. So to me, that raises the question of when did the Chukchi Borderland form? When did it get its primary architecture? This is the gravity map, just showing the Chukchi Borderland here and across the Canada Basin. This is the shelf edge anomaly there. So this is the seismic record, of course, across the Chukchi Borderland, a very rugged topography, and at least in the northern part, not many sediments. There's perch basins here, but really it's a pretty sediment-starved environment. I showed you that graben in a different slide earlier. This is where that profile is located. It's on a gravity low anomaly that's actually subparallel to the main orientation of the Chukchi Borderland. This would be basement. It's showing the same kinds of highs and lows that we see here. There's probably perched basins in here. But this one has been totally sedimented over, totally covered. And given, and this is a stretch, but given the similarity of this, which is older than the basin, because it's clearly in where the oldest sediments are, I would suggest that perhaps the main architecture of the Chukchi Borderland was inherited as part of the rifting, and that the young deformation is just a modest kind of overprint on it. But anyway, that's just a flavor. There's still lots to do, and I'm happy to answer any questions. So thank you very much.
When you used the air guns, did you have to do anything special about marine mammals?
We did. We had to have, because it was a Canadian vessel, we had to follow Canadian law when we were inside the Canadian EEZ or in international waters. There was only one cruise when we came into the US EEZ, which we then had to go through the full NOAA permitting for that. But it turns out that NOAA recognizes the Canadian environmental process the same way that they recognize ours. So We had to go through all the paperwork. We had to work with the native community to assure them that we were not going to be chasing the rails away, because of course the native community hunts the rails. I think we were probably had an easier time than a lot of industry. Our lines only came into about 2,000 meters of water on the Beaufort Shelf, whereas industry typically operates right up on the shelf, so they come under much greater scrutiny. So anyway, we had lots of, they're now called protected species observers. They used to be marine mammals observers.
Where's the hyphen?
Yeah.
So how much of the Canadian basin is going to be exploitable based on this? I mean, you talked at the beginning about this sort of flexible border of where you can exploit resources.
What has to happen from here is Canada has to show where their extended continental shelf goes. The US has to show where their extended continental shelf goes, but then there's going to be a boundary negotiation to actually separate it out. Now, in terms of exploitable resources, this is a harsh environment, and so whether there's oil and how much oil and gas goes into the deep water portions of the basin is for somebody else to figure out. The North Slope, which is just the feather edge of all of these sediments, is one of the most prolific oil-producing regions in the U.S. right now. So there's every good reason to think that there's oil offshore, but it hasn't really been adequately explored or and certainly not drilled. So it's a long time from certainly commercial development of energy resources.
But it potentially would be.
It potentially
if it could be done technologically.
Yeah.
There didn't seem to be much evidence over the 100 million year timescale that you were showing in the lines of alterations in input of material from river systems and things that might have been present over that extended time period. So I'm just wondering why it seems so unaffected by any kind of boundary inputs. It seems to be. Do you think that deposits are largely pelagic in? What kind of material is it, I guess?
Well, there's certainly a lot of mud. I mean, it probably on land, the lower Cretaceous has a lot of clastic, and then it turns into pretty fine-grained stuff pretty quickly. Our data set didn't really come up far enough onto the slope, and we didn't reach the shelf to be able to identify river systems. We only had 3 lines, and again, we had to maximize data acquisition for law of the sea, not necessarily for science. The Mackenzie River is clearly the exception to that, and that clearly dominates the whole Canada basin. I think what was surprising to me is that there was no evidence that the Chukchi Borderland was above sea level and produced significant deposits like you might infer from the continental margin. I think on Southern Alpha Ridge we have some lines that show local debris, mass transport deposits that could indicate that parts of Alpha Ridge were above sea level. But again, we were only dealing with the very southern edge of Alpha Ridge in our data. We weren't where the main part of the large igneous provinces, which would have been the part that was above sea level. So, good question. But certainly, I think there's a lot of interpretation of that on the Chukchi Shelf of younger processes. But we haven't fully linked to that.
Is there any more recent evidence of hydrothermal, or hydrothermal vent type locales in that
Well, there's a
area?
lot on
Could
the
you share
Gapple
that?
Ridge. There's a lot of stuff on the Gapple Ridge, which is young. There's been, I think, ROV evidence that sees hydrothermal stuff there. There just hasn't been much work done in the
Right.
Arctic here. Now, on
Yeah.
some of the dredges that were done, they're thick crusts. And those are being looked at for what the mineral content is. And is, from what I understand, and this work is being done by Jim Hine out at US-GSC Mineral Park, that it's not dissimilar to some of the crusts that they see in the Pacific, and could potentially be another economically viable resource.
Okay, well, thank you, Debbie, for giving us some insight into.
So when
Person, how much effort is going into this.